Hello everyone, myself Dr. Santanu Kundu. I welcome you all to this lecture of soft computing techniques. This is the fifth lecture of module 12. So last class we have discussed adaptive neurophagy systems. In this class we will try to understand ant colony optimization. Ant colony optimization is a nature-inspired optimization algorithm based on the foraging behavior, that is searching for foods etc. of ants. It was first introduced by Marco Dorigo in 1992 and is often used to solve complex combinatorial optimization problems such as finding the shortest path in graph, scheduling tasks, or solving the traveling salesman problem. So this is basically the concept of ant colony optimization. So basically ant move from nest and in searching of foods. So this is they are moving from nest to foods. Now in between there are some obstacles. So some ants will move to this direction, some ants will move to that directions. Now when they are moving, they are depositing some pheromone in their trail. So they are depositing some pheromone. So ants follow the path where there are more pheromone deposited. So if there are more ants, then ultimately nobody will come to this side. Everybody will come to this side. So this is the concept of ant colony optimization. So now check it. So key concept of ant colony optimizations. First one, ants and pheromones. So ants in the algorithm simulate real world ants. They search for food by moving through a graph and they leave a trail of pheromones on edges they traverse. Other ants are attracted to stronger pheromone trails. The pheromone levels guide the ants towards better solutions over time, as ants will generally prefer paths with higher pheromone concentration. Second is positive feedback. Positive feedback occurs when ants are more likely to follow paths with higher pheromone levels, reinforcing those paths and making them even more attractive to subsequent ants. Evaporation of pheromone. Pheromones decay over time, simulating evaporation. This helps avoid premature convergence to suboptimal solutions, as less frequently used paths will lose pheromone strength. Last one is the exploration versus exploitations. Exploration refers to the ants trying new paths, while exploitation refers to them reinforcing known good paths. A balance between these two is essential for the algorithm to find the global optimum. Now, ant search process and explore search space by traversing the graph and depositing pheromone along their paths. When they complete the journey or when a task like test page finish, they evaluate the quality of the solution and this evaluation guides the pheromone update process. Now, steps in ant colony optimization algorithm. So first one is initialization. Initialize the pheromone levels on the edges, often randomly or with a small constant value. Set parameters like the pheromone evaporation rate and the number of ants. Ants movement. Each ant builds a solution by moving from one node or state to another based on pheromone levels and possibly other factors like heuristic information. Step 3, pheromone update. After all ants have completed their paths, the pheromone on each edge is updated. This involves both pheromone evaporation to reduce the strength of the pheromones and pheromone deposit by ants based on the quality of the solution they found. Better solution get more pheromone. Stopping criteria. The algorithm repeats the process for a set number of iterations or until some convergence criteria is met. As for example, when the solution does not improve after several iterations. Applications of ant colony optimizations. Traveling salesman problem (TSP). Ant colony optimization can be used to find the shortest possible route that visits each city exactly once and returns to the origin city. Vehicle routing problem. SEO is used for optimization in logistics where a fleet of vehicles must be routed efficiently. Job stop scheduling. In manufacturing, SEO can help optimize the scheduling of tasks to minimize completion time or maximize throughput. Network routing. It can help in designing optimal routing protocols for communication networks. Advantages of ant colony optimization. It can solve complex optimization problems with large solution spaces. The algorithm is flexible and can be applied to a wide range of problems. End-to-end optimization is robust and adaptable to changing environments. Disadvantage of SU: SU can be slow and computationally expensive, especially for large-scale problems. It may require fine-tuning of parameters like evaporation rate, number of ants, etc. to get the best performance. There is a risk of algorithm getting stuck in local optima if not properly tuned. So this is mathematical formulations. So an ant will move from node or CTI to node or CTJ with probability. So this is Pij probability that is equal to tau ij to the power alpha eta ij to the power beta summation of k belongs to allowed nodes or cities tau ik to the power alpha into eta ik to the power beta. Where tau ij is the amount of pheromone in age I to j, eta ij is the desirability of age ij, sometimes it is 1 by dij, that is the inverse of the distance between cities or nodes. Alpha is a parameter to control the influence of tau ij, beta is the parameter to control the influence of eta ij. Now update pheromone tau ij equal to 1 minus rho tau ij plus summation k equal to 1 to m delta tau ijk, where delta tau ijk is q by lk if and k travels on edge I to j to 0 otherwise. Delta tau ijk is pheromone quantity laid on edge ij by the kth ant, where lk is the two length of kth ant, q is some constant, rho is evaporation rate, and m is the number of ants. So this is the example. In this example, we are just calculating the probabilities. So you know the probability formula P ij is tau ij to the power alpha eta ij to the power beta by summation of k belongs to the allowed cities. So tau ij whole to the power alpha eta ij whole to the power beta eta ij is 1 by lij. So here there is some traveling salesman problem. So here four cities A, B, C, D. So from A to D or D to A, this cost is 4. D to C or C to D is 1. A to C is 15. C to A also 15. So these are the cost. Initial pheromones all are 1. So here tau ij is 1 by 4. So from here we are from C, we want to move from D, we want to move from A or B. So we want to find the probability of all these. So now from C to D. So here eta is 1 by 1. So if CID is PCID, you know the formula for that. So that will be tau CD into to the power alpha eta CD to the power beta by from C. So that will be summation of all this from C, because there are three paths. So from C to D to the power alpha eta C to D to the power beta and plus summation of tau to C to A to the C to A to the power alpha plus eta C to A to the power beta again plus tau C to B to the power alpha eta C to B to the power beta. So eta CD here you can write 1 by 1, eta C to A is 1 by 15, eta C to B is 1 by 4 and tau is 1, and we are assuming alpha equal to 1, beta equal to 1. So that is 1 into 1 by 1, so you'll get 0.7595. Now C2A is 1 into that, 1 into 1 by 15 by summation of all this. So that things here also same thing. So as probability is more here, so it will select D from C. So this is the example of probability. Now calculation for pheromone updates. So here this is the cost matrix. So A to D is 4. Similarly of A to A not required, A to B is 5. So A to C is 15, A to D is 4. Similarly all these are given. Here is the pheromone matrix. So here A to A is 0, so A to B is 4, A to C is 10, A to D is 3. So these are the pheromone matrix. Now you know that is tau ij equal to 1 by Lk, kth and travels on the edge ij, it is 0 otherwise. So tau ij is summation of all this without vaporization or without evaporation. Now it is with evaporation. So this is the formula. So here we assume that the path, so there is two arms, one is this arrow, one is that, so it follow the path A to D to C to B to A. The total length is 14, so 4 plus 1 5 and 9 14, so that is 1 by 14. L2 is A to C to B to D to A, so here it is total 31, so it's 1 by 31. So tau is summation of all this. So here the summation for 1 and 2 and there is 2 ends. So here is m equal to 2. So there are 2 ends. So need to summation of all these paths here. So there are two ends travel. So it is 1 by 4 plus 1 by 31. Here it is only 1 ends 1 by 14. Here it also both ends. So 1 by 4 plus 31. This is 1 by 31. This is also 1 by 31. And this is 1 by 14. So this is the tau ij. Now if we apply the formula, so tau is equal to 0.5, this is rho is 0.5, so 1 minus 0.5 into initial is there is 1, so this is the initially tau ij, so this is the formula where we get that pheromone. So here initially all the pheromones are given here, so this 2 is 3 given, so in this way we calculate the pheromones here. Tau ij, so 1 minus root tau ij from D to A. So check the initial pheromone. So initial pheromone from D to A, it is 3. So there it will be into 3. So here it will be into 3. Initial pheromone is there. So here this is 0.5, here is 1 1. Just you need to check the initial pheromone, apply the formula. So tau ij is the initial pheromone, so it is 3. And if you go back here, then you will get it pheromone is 1, initial pheromone is 1. So here also will be the 1 is there. Here it is also 1. In this way you will just try to, here also 1. In this way you try to calculate the pheromones. So just you check with pheromone. Check with pheromone values. So this is the thing. Now we want to solve one question based on ant colony optimization. So question is that minimize x1 square plus x1 into x2 plus x2 square, where x1 there are four possible solution for x1 1 2 3 4, for x2 three possible solution 3 4 5. So we initialize four ants for x1. These are x1j, j is 1 2 3 4, I mean x11 x12 x13 x14. We consider x11 equal to 1, x13 equal to 3, x14 equal to 4. Similarly, consider 3 ants for x2. So x21 equal to 3, x22 is 4, x23 is 5. So we call initialize the ants. Next here eta I is equal to 1, because see this is x1, this is x2, so only one path. So two length is 1. So that is 1 by dij, so eta is 1. We assume equal pheromone for each ants. So tau I is equal to 1. So tau ij 1, eta ij 1. So now formula is simple become P1j equal to tau ij summation of tau ij. So here is for 1 it will be P1j, and it is summation of j equal to, if you write 1 here, it is j equal to 1 to 4. For second is P2j, so that is tau 2j by summation of I equal to 1 to 3, because there are 3 ants, so it is tau 2j. So here, so the probability for each ants of x1 is P1j, so each values are 1 1 1, so you get 1 by 4. Probabilities for each and for x2 is 1 by 3. Similar way. Now for roulette wheel selection with random numbers and for x1, so that is x1, so that is the cumulative probability. So x1 is 0 to 0.25, for x1 to 0.25 to 0.50, for x13 0.50 to 0.75, for x14 0.75 to 1. And for x2, x21 is 0 to, here is probability 1 by 3, so it is 0 to 0.33, x22 is 0.33 to 0.67, x23 is 0.67 to 1. Now we need to generate random numbers, so there we generate 4 random numbers. So this is 0.60, first random number, it belongs to here, so x13 is selected, and 3 is selected. Second random is 0.99, so this belongs to this interval, so x14 is selected. Third is 0.58 here also, so x13, that means 3 selected. X17, so here, so x11 is selected. Similarly for AND 2, random number 0.68, so here x23 selected. 70, here x23, that is 5 selected. 0.41 is x22 here, so 4 is selected. So these are the selections. So here is 3 ants, here is 3 ants, here is 4 ants, so total possible solution is 12. So possible sets of solution x13 to x23, x13, x23, x13, x22 is equal, how we getting, just like that, x13 here, so x13, x23, x13, x23, x13, x22, x14, x23, x14, x23, x14, x22, x13, x23, x13, x23, x13, x22, x11, x123, x11, x23, x11, x22. So just like Cartesian product, so we got 12 solutions. So and values are 3 and 5. For x1 and 3, this is 5. Put the formula here, so it will be 3 square 9 plus 15, 9 plus 15 plus 25, so it is 49. So here also 49, here is 3 4, so 37, 4 5 61, 4 5 61, 4 4 48, 3 5 is 49, 3 5 49, like that. So you have seen this is the best solution, this is the odd solution, because we are solving minimize problem. So now iteration 2, assume the evaporation rate rho equal to 0.4, Q constant is 2, update pheromone for each and we increase the pheromone for x11, x22, as this give the best solution x11 and x22. Okay, so now evaluate pheromone for other ends. Consider tau I rho delta tau. Consider delta tau equal to Q into best by odds. So Q is 2 summation. So but summation not required because best appear only one time. So that is 2 into 21 by 61. So ends for x1, x11, 1. So that is pheromone 1 minus 0.4. Initially is 1. So 1 minus 0.4 into 1. So it is and plus this tau ij. So 2 into 21 by 61. You will get 1.289. For x1 to 2, that is 1 minus 0.4 into 1. That is 0.6. For ant 3, you will get same thing. For ant 4, same thing. Here also you will get for and x21, so that is 1.04, so that is 0.6, x22 is 1 into 1 minus 0.4 into 1 to 21 by 61, 1.29, same like that. Here also 6. So the solution, the base solution have more pheromone. Okay, now update probabilities. So probability is same formula, so that is the uh, here you will get sum is but there 1.289 by summation of 0.6, 0.6 plus 0.6. So that is the probability for x11, x21 is 0.194, x13 0.194, that is 0.194. So this is the highest because it have the more pheromone. Similarly this is also the highest, so this is probability. So we need to do selection by roulette wheel, same thing, using random number, possible set of solutions, need to do update pheromone to get better solution, and we may need to repeat few more iterations to get the best solution. So that is basically the AND cloning optimizations. Let's check another solution. So this is the problem. So we have 4 cities labeled as C1, C2, C3 and C4, and we need to find the shortest route that visits all cities exactly once and return to the starting city or the origin city. So here the city C1. So from C1 to C1 distance is 0. Dij represent distance. So this is 0. From C1 to C2 10. From C1 to C3 is 15. From C1 to C4 is 20. From C2 to C1 is 10. From C2 to C2 0. From C2 to C3 is 35. C2 to C4 is 25. And this is symmetry matrix, so same thing, 15, 35, 0, 30, 20, 25, 30, 0, so same thing. So this means, for example, distance between C1 and C2 is 10, and the distance from C2 to C3 is 35, and so on. So SO parameters, so here we consider three ants. Number of iterations 3, alpha is 1, beta is 2, initial pheromone is 1. So let's go step by step solutions. So that is the initial pheromones. So now add moment for fast iteration. So that is the formula P1 Pij equal to tau ij to the power alpha, eta ij to the power beta, k allowed cities, tau ik to the power alpha, eta ik to the power beta, where tau ij is the pheromone level on the edge between cities I and j. Eta is 1 by di is the inverse of the distance between cities. Alpha beta control the importance of pheromones and the distance respectively. So ant 1 movement starts at C1. So next city we need to choose for the probability. So next C2 from C1 is available, C2, C3 and C4. So we need to calculate this formula. P C1 C2 is tau C1 C2 to the power alpha, eta C1 C2 to the power beta, and summation of all C2, C3 and C4, because this is the allowed cities. So now n C1 C2 is distance, so 1 by dij, so it is 1 by 10 0 1. In C1 C3 1 by 15, so this is, and C1 C4 is 1 by 20. So calculate the probability from P C1 and C2. So this is the probability for from P C1 and C2. So if we take the calculation, get 0.591. Similarly, we can formula for P C1 and C3 like this. So then P C1 for C4 like that. So and we'll move from C2 because this is the highest probability. Now similarly for AN2 movement start at C2. So similarly for AN2 starting at C2, the available cities C1, C3 and C4, using the same process we will get the probability for each path. So here this is the highest, so AN2 will move C1. So and 3 also same way, so it will also move to C1. So similarly to complete the tours, so tour from C1 to C2 to C3 to C4 to C1 and 1 go like that, and to C2 to C1 C4 C3 C2 and 3 C3 C1 C2 C4 C3, so they'll move like that. So now we need to do the pheromone update. So pheromone deposition, so here assume q equal to 1. So tau ij is q by L path. So for ant 1, the distance between all the cities C1, C2 10, C2 to C3 35, C3 to C4 30, C3, C4 to C1 to 95. So tau ij is 1 by 95, that is 0.0105. We need to calculate for ant 2 and ant 3. Second step is pheromone evaporation. So the pheromone on each edge evaporates by factor rho equal to 0.1, so that the update rule is tau ij equal to 1 minus rho tau ij plus delta tau ij. So delta tau ij is here q by L path. So q by L path. So that is the pheromone. So it is 0.9105. So we need to perform update for all edges, and the pheromone matrix will update it, and the same thing we need to do. So next is we repeat for next iteration. So this process repeats for specified number of iterations. After multiple iterations, the ant will converge toward the shortest path as pheromone accumulates along the best routes. So this is a simplified example. In a real world application, the number of ants, iterations and pheromone update formula might be adjusted to optimize the algorithm performance for large problems. Each iteration refines the search with ants converging on the shortest possible path influenced by the pheromone updates. So in this class, we have understood ant colony optimization technique. So question is today's class is that find maximum value of x1 square plus x1 x2 plus x2 square where x1 is same thing, 1 2 3 4, x2 3 4 5. Solve it by and colony optimization technique. Okay, so these are the reference of today's class. Thank you.